In this video we are going to look at the FP2 work on complex numbers, which concentrates on the statement and applications of de Moivre's theorem. The WJEC specification states that we should know and be able to use de Moivre's theorem, be able to apply it to trigonometry, and also be able to apply it to finding the nth roots of a complex number. So de Moivre's theorem states that if z is cos theta plus I sin theta, then z to the n is the same thing as cos n theta plus I sin n theta. In terms of applications, it enables us to calculate powers and roots of complex numbers. So if we know the modulus of w is r and the argument of w is theta, then we can write w to the n is the same thing as r to the n times cos n theta plus I sin n theta. And if we use the shorthand of representing w by r comma theta, modulus then argument, then we can say that w to the n has a modulus of r to the n and an argument of n theta. And we can also use de Moivre's theorem to find nth roots of a complex number. De Moivre's theorem also has some powerful applications to trigonometry, and we need to be able to use de Moivre's theorem to prove results such as these, and also we should be able to use de Moivre's results to deal with powers of trigonometric functions, as shown in the example here. So let's now have a look at some exam examples on de Moivre's theorem. So for the first one, we are given the complex number z equals minus 1 plus I, and to start with we have to find the modulus and argument of z. It's always a good idea to start off with a quick sketch diagram. Z is the complex number minus 1 plus I, so the modulus of z is simply the square root of minus 1 squared plus 1 squared, so that's root 2. The argument of z is easily found if we first of all think about that angle theta, and the little triangle that we've drawn there is an isosceles triangle with sides 1 and 1, but it's also a right angle triangle, so theta must be 45 degrees or pi by 4. So the argument of z must be 180 minus theta, so that's 135 degrees, or if we like 3 pi by 4. So we've got the modulus of z is root 2, and the argument of z is 135 degrees or 3 pi by 4. And for the rest of the question we'll keep it working in radians. So we've now got to find the 3 cube roots of z, giving them in the form x plus iy. So let's suppose that w with argument r with modulus r and argument theta is a cube root of z. Then we want w cubed to equal z. Well, we know the modulus of w cubed is r cubed. We know the argument of w cubed is 3 theta. We know the modulus of z is root 2, and we know the argument of z is 3 pi by 4. So we want r cubed to be the same thing as root 2, and we know that we want 3 theta to be the same thing as 3 pi by 4. So we've got r cubed must be root 2, in other words 2 to the half, so r needs to be the same thing as the 6th root of 2, or 2 to the 6th. We also know that we want 3 theta to be the same thing as 3 pi by 4. Now that's only going to give me one value for theta, so we need to stop and think for a moment or two. And if we've got 3 theta equals 3 pi by 4, 3 pi by 4, if we add 2 pi onto it, is really the same thing as 11 pi by 4. And adding 2 pi on again is the same thing as 19 pi by 4. So we've got 3 theta could be 3 pi by 4, it could be 11 pi by 4, it could be 19 pi by 4. Dividing by 3, we've got theta is pi by 4, or 11 pi by 12, or 19 pi by 12. So we've got 3 possible forms for W. It could have a modulus of 2 to the 6th and an argument of pi by 4, which means that W is 2 to the 6th cos pi by 4 plus I sin pi by 4, which then gives me 0.794 plus I times 0.794. Or similarly, we could have W having a modulus of 2 to the 6th and an argument of 11 pi by 12, which gives me W equals minus 1.084 plus 0.291i. Or finally, we could have W having a modulus of 2 to the 6th and an argument of 19 pi by 12, which gives me W equals minus 0.291 plus 1.084i. Moving on to the final part of the question, we know that the modulus of z is root 2 and the argument of z is 3 pi by 4, so z to the n is going to have a modulus of root 2 to the n and an argument of n times 3 pi by 4. If we want z to the n to be a real positive number, now a real positive number has an argument of 0, or 2 pi, or 4 pi, or 6 pi. We certainly need n times 3 pi by 4 to be a multiple of 2 pi. Now 3 pi by 4 times n is the same thing as 3/8 n times 2 pi. So we need 3/8 n to be an integer, a positive integer. And the smallest value of n that will make 3/8 n, the smallest integer value of n that will make 3/8 n an integer is n equals 8. The marking for this question, we had 1 mark for finding the modulus of z and then 2 marks for obtaining the argument of z. There are 3 marks for finding the first of the 3 cube roots, 2 marks then for the second cube root, and another 2 marks for successfully obtaining the third cube root. And then for part C, we needed to realise that 3/4 pi times n needed to be a multiple of 2 pi, and then to spot that n equals 8 to obtain the 2 marks. So let's move on to a second example now, which comes from the 2010 paper. We have to start off by writing de Moivre's theorem for n equals 5, and hence show that sine phi theta divided by sine theta can be written as a times cos to the 4 theta plus b times cos squared theta plus c. So let's start with that. De Moivre's theorem for n equals 5 states that cos theta plus I sine theta to the power 5 is cos phi theta plus I sine phi theta. At this stage, it will save us a lot of work if we introduce a shorthand. And the shorthand is simply going to replace cos theta by c and sine theta by s. So the statement of cos theta plus I sine theta to the power 5 equals cos phi theta plus I sine phi theta simply becomes c plus is to the power 5 equals cos phi theta plus I sine phi theta. Using Pascal's triangle, or equivalently the binomial expansion, we can expand the left hand side and we'll get 1 lot of c to the 5 plus 5 lots of c to the 4 times is plus 10 lots of c cubed times is squared plus 10 lots of c squared times is cubed plus 5 lots of c times is to the 4 plus is to the 5. And that lot still equals cos phi theta plus I sine phi theta. We now need to simplify the left hand side. The first term remains c to the 5. The second term there is 5 c to the 4 s times I. Now the next term we've got is 10 c cubed I squared s squared, but I squared is minus 1. So that simply becomes minus 10 c cubed s squared. The next term along, we've got 10 c squared I cubed s cubed. I cubed is I squared times I, so that's minus I. So that term is minus 10 c squared s cubed I. Next term along, there we go, is 5c I to the 4 s to the 4, but I to the 4 is 1. So that term is 5c s to the 4, and then the final term is is to the 5, and I to the power 5 is just the same thing as I, so that's is to the 5. Now in the question we're not interested in the cos phi theta bit, we're only interested in the sine phi theta bit. In other words, we're only interested in the imaginary part of the right hand side. So let's also focus in on the imaginary parts of the left hand side. So there they are underlined. So the imaginary parts on the left hand side must equal the imaginary part of the right hand side. So we have 5c to the 4 s minus 10 c squared s cubed plus s to the power 5 must equal sine phi theta. So there's our result written down again. Now we want the value of sine phi theta divided by sine theta. So dividing by sine theta now gives us sine phi theta divided by sine theta is 5c to the 4 minus 10 c squared s squared plus s to the power 4. Now we need to remove the s squared and the s to the 4 from the right hand side if we're going to end up with anything looking like the target expression. But we know that cos squared theta plus sine squared theta is always equal to 1. So c squared plus s squared equals 1. So that means I can replace s squared by 1 minus c squared. And s to the 4 is simply s squared squared. So that's 1 minus c squared squared. So we've got sine phi theta divided by sine theta is 5c to the 4 minus 10c squared times 1 minus c squared plus 1 minus c squared squared. Now there's a couple of obvious lines now of algebraic expansion to go through, which brings us down to sine phi theta divided by sine theta is 16c to the 4 minus 12c squared plus 1. And remembering that c stands for cos theta, we have sine phi theta divided by sine theta is 16 cos to the 4 theta minus 12 cos squared theta plus 1, which is the required result with a equals 16, b equals minus 12 and c equals 1. Now, as theta tends to 0, we know that cos theta tends to 1. So the right-hand side is going to get closer and closer to 16, take away 12, plus 1, which is 5. So in other words, as theta tends to 0, sine phi theta divided by sine theta tends to 5. So the mark scheme for this question, well, first of all, there's 1 mark for simply stating de Moivre's theorem, and then there are 2 marks for the expansion of the cos theta plus I sine theta to the power 5. We then need to look at the imaginary terms and pull out the sine phi theta terms, and then divide by sine theta to obtain the expression that we had, which was 5c to the 4 minus 10c squared s squared plus s to the 4. That gets us another 2 marks. Obtaining the final answer, 16 cos to the 4 theta minus 12 cos squared theta plus 1, gave us another mark. And then we needed to let theta tend to 0, realise cos theta tended to 1, and then deduce that that meant that sine phi theta over sine theta tended to 5 to obtain the final 2 marks. Now let's move on to our final example for this video, which comes from the 2011 paper. We're told that z is cos theta plus I sine theta. We've got to show that z to the n minus 1 over z to the n is 2i sine theta, 2i sine n theta, and we've got to obtain a similar expression for z to the n plus 1 over z to the n. Well, this z is cos theta plus I sine theta. De Moivre's theorem tells us that z to the n is cos n theta plus I sine n theta. 1 over z to the n is 1 over cos n theta plus I sine n theta. To divide by a complex number, we need to multiply the top and the bottom of the fraction by the complex conjugate of the denominator. So we multiply top and bottom by cos n theta minus I sine n theta. The top stays just as cos n theta minus I sine n theta. The bottom simply becomes cos squared n theta plus sine squared n theta. But cos squared n theta plus sine squared n theta is just equal to 1. So we know that 1 over z to the n is cos n theta minus I sine n theta. So there are the 2 results I've got for z to the n and 1 over z to the n. If we simply take the second result away from the first result, we get z to the n minus 1 over z to the n is 2i sine n theta. And if we add result 1 and z2, we get z to the n plus 1 over z to the n is 2 cos n theta. So moving on to part B now. It's asking us to consider z minus 1 over z to the power 4. Well, the first thing to do is think about what z minus 1 over z represents. Well, z minus 1 over z is a special case of the result of for z to the n minus 1 over z to the n with n equals 1. So we know that z to the 1 minus 1 over z to the 1 is going to be 2i times sine of 1 theta. In other words, we know z minus 1 over z is simply 2i sine theta. So z minus 1 over z to the power 4 is going to be the same thing as 2i sine theta to the power 4. Using Pascal's triangle, or indeed the binomial expansion, the expansion of the left hand side is 1 lot of z to the 4 plus 4 lots of z cubed times minus 1 over z plus 6 lots of z squared times minus 1 over z squared plus 4 lots of z times minus 1 over z to the power 3 plus 1 lot of minus 1 over z to the power 4. Looking at the right hand side, we've got to just multiply 2I sine theta. Sorry, we've got to raise 2I sine theta to the power 4. So that's 2 to the 4, which is 16, times I to the 4, which is 1, times sine theta to the power 4. So the right hand side is 16 times sine to the power 4 theta. Let's tidy up the left hand side. The first term is just z to the 4. The second term is minus 4, and then I've got z cubed divided by z, so that's minus 4z squared. The third term, there we go. The third term there, we've got 6, then we've got z squared times minus 1 over z all squared, minus 1 over z all squared is 1 over z squared. So we've got 6 times z squared times 1 over z squared, just gives me 6. Moving to the third term, minus 1 over z cubed is minus 1 over z cubed. Times by z is minus 1 over z squared, so the whole thing comes out to be minus 4 over z squared. Minus 1 over z to the power 4 just ends up giving us 1 over z to the power 4. So we've got z to the 4 minus 4z squared plus 6 minus 4 over z squared plus 1 over z to the 4 equals 16 sine to the 4 theta. Now just look at this carefully. We've got z to the 4 plus 1 over z to the 4 there. And we know that z to the 4 plus 1 over z to the 4 is 2 cos 4 theta. And we can do something similar with the z squared terms. So we'll just rewrite the left hand side. First of all, collecting together the z to the 4 plus 1 over z to the 4. Collecting together the z squared and the 1 over z squared term. So we've got z to the 4 plus 1 over z to the 4. Take away 4 lots of z squared plus 1 over z squared. Add 6 must equal 16 sine to the 4 theta. Using the result we've already shown, we've got z to the 4 plus 1 over z to the 4 is 2 cos 4 theta. Z squared plus 1 over z squared is 2 cos 2 theta. So we're very close to the expression we want. We want to show that sine to the 4 theta is equal to something, so we need to divide through by 16. So dividing through by 16, we obtain 1/8 cos 4 theta minus a half cos 2 theta plus 3/8 is sine to the 4 theta, which is exactly what we want with A equals 1/8, B equals minus a half, and C equals 3/8. Now the marking for this question, first mark again for simply writing down de Moivre's theorem for z to the n. 2 marks then for dealing with z to the minus n, and then 2 more marks for obtaining the given expression for z to the n minus 1 over z to the n, and for obtaining the expression for z to the n plus 1 over z to the n. And then for part B, we had 2 marks for doing the expansion of z minus 1 over z to the power 4. So we had 3 marks for doing the expansion of z minus 1 over z to the power 4, and then linking that up with the previous results gave us the method mark and the answer mark for the total of 5 marks.